Okay. Yep. So we come to the next chapter. Who hasn't got one that you take one here? From the handout today. From the handout distributed today. Okay? Now we talk about one new thing that is friction. From chapter 4, we have learned two types of supports. One type is pin, right? This is the one on the left is called pin support. And what is this type of support? Roller. So on the left, what is the difference between the pin support and the roller support? For a pin support, we cannot move to the left and to the right. And here for the roller support, we can always move to the left and to the right, right? And without any forces. That if you put a small force here, then it will go to the left all the way along. But in reality, we usually do not have rollers. We always have this type of supports. That is, if we push it to the left, then it will go to the left a bit, and then it will stop there. It will stop there. So here we have in reality. Usually we have dry friction between the structure and the floor. So this is called dry friction 摩擦啊. So here take a look of this word friction. Friction 摩擦哈 but 阻力 but does anybody know what is this one? Friction. 少说哈. So remember we have an R here. Is that okay? If we say if we do not have an R, then it becomes 小说哈. Now, and we have the types of friction. Of course, in our course, we talk about dry friction 摩擦, but in machines, we have another types of friction, which is called viscous or fluid friction. This will be covered, or we will talk about this in year 3 fluid mechanics. So here is what is this viscous or fluid friction? Just think about your scooter or your bicycle. That you need some so you need this, right? 润滑油这样子. So what's the English of this? It's one type of 润滑油 WD-40 And generally these are called lubricants. So one example is WD-40, of course. So you have lubricant. So we talk about dry friction here, but remember in year 3 you will for mechanical engineering students that we have this one in year 3. Sorry. After you make these notes, then we draw the free body diagram of a block of a mass block here. And for a mass block here, we have so it has a, let's say we have it is put on a is put on a floor with friction. Now here, before we try to push this block, if it is at best it is has equilibrium when it is on the floor, then which forces can we draw? Suppose we have a force of W. What else can we draw before if it is not moving? We have a force of gravity W here. What else? Any other forces can we draw on this free body diagram? Are there any forces you can draw? Or if you have only W equals to mg, then it will fall down, right? But why is it remain at best here? Because we have reaction force R here. Now we have if we want to push the block to the right, then we have a force P here. But because we have friction, that we have friction F here. So these are the 4 forces I will talk about in the next in this week. After you draw the free body diagram, we go down here. Let's have a look of the relationship between F and P. And P. So we have, let's look at let's talk about when P is very small first. So if, let's say we have friction here. Let's say we have friction here. So I think I put my cup here. So it is at rest on the floor. If we have a very small force, it does not move because we have friction, right? If we have only a very small force, then it will not move because we have friction from the floor. Only if the force is higher than some value, that it goes on to move along the desk. So you can try take your phone and then you push it. Then if the force is very small, then it will not move. And if only the force is high enough, then it will move. Okay. So if P is very small and if it does not move, what can we say about the relationship between P and F? If the block is at rest, so the summation Fx is equal to 0, right? If it does not move. If it does not move, summation F equal to 0. What can we say P, the relationship, and F? What can we say about this? In this case, P is equal to F, okay? Because summation F equal to 0 and it does not move. So let me put one dotted line here. P is equal to F here. And we go from here, let's say we go from here. Now, but if the force is high enough that the block starts to move or start to accelerate. So in this case, P is larger than F. If it starts to move, okay. If it starts to move, then P will be higher than F. So you don't drive first. But after that, it will go in this direction. But we have found that the relationship actually looks like this. Sorry. The relationship actually looks like this. So for this part, for the part on the left, it is this part is B, no motion. So the block does not move in this region. It is easy to understand that this is P is equal to F. Okay. In this case, P is equal to F. And on the right, we know that there is motion. The block starts to move to the right. So then in this part, this is called motion. And so copy this figure first. P is larger than F, so there is motion. We have two more things to write down, and I'll talk about this in a minute. the thing we look at is we find that the friction, the maximum friction when it has no motion is higher than the friction when it has motion. This is quite interesting, huh? So if the maximum friction is here, but after the block is moving, the friction is actually lower. And these two values are related to, actually they are related to R. We will say this one is equal to mu S times R, and this one is mu K times R. And these two values are called mu S and mu K are called coefficient of static friction and coefficient of kinetic friction. And this one, if you want to know the Chinese, that it will be this one. But of course, I think the Chinese is not that easy. Not much easier. Here, and we have B and D. That at this point, and from there is no motion, and it goes to a very high level of friction before it drops and moves. We have this situation is called motion impending. And this one, this word impending is can be, you can understand it as this one. Wait a minute, I give you. So this is the graph between F and P. And remember this, and I may ask you to draw it in examination. And for usually for this kind of graphs, remember it is you can always remember the shape. You can always remember the shape. That's 90% of your seniors that can remember the shape, but only half of your seniors remember the quantities in x and y axis. Instead, okay, it is important to always memorize the x and y axis. You will have no problem remembering getting the shape right, but remember what is on x and y axis.